In today's video, I'm going to go over an example of problem you'll see in the Mechanics 2 class on Mohs circle. So most of the work here is already worked out for the first 4 parts. However, I'm going to quickly go over them, as this is more of kind of a review and practice as a harder example problem you'll see. So let's begin. So in a Mohs circle, they're going to give you a stress element with different normal stresses and the shear stress. So as we can see here, it is 4 KSI tensile in the positive y direction, and then 12 KSI tensile as it's going outwards in the x direction. As we can see, the shear stress is clockwise in the x direction, associated with these two signs, and counterclockwise in the y direction of 5 KSI. So in this question, we'll be going over constructing the Mohs circle, determining principal stress, determining the max in plane shear, showing on a properly oriented stress element for both of those two scenarios, and then finally evaluating the 3 stress failure theories for this. So most of it's already been done. However, looking here, when you draw a Mohs circle, it's important to note for the shear stress, above is going to be clockwise, and then below is counterclockwise, and then for sigma it's positive and negative. So this is a fully finished Mohs circle for this question. So to begin on Mohs circle, you first have to find the center. These equations I have over here are going to help, and they should most likely be given to you. So it's going to be sigma x plus sigma y divided by 2, which is just 4 plus 12 divided by 2, which is just going to equal 8 KSI. That is why I drew the center here is 8 KSI. After that, you have to figure out the radius. That is just going to be this long equation. It's done using Pythagorean theorem. We won't cover that. However, it's going to work out to 6.4 KSI, because it's going to be 8 over 2 squared plus 25, as you're going to get 12 minus 4 is going to be 8, and then etc., etc. So that's how you get the radius. After that, you have to figure out to actually draw a circle. So you know the radius is going to go straight up here. It's going to go, it's going to be constant everywhere. So using those two, you can draw the circle. And then next, you actually have to draw our current stress element along this Mohs circle. So we know sigma x is going to be positive 12 and a clockwise rotation with the shear stress. So on this circle, we have positive 12 for that sigma x, as we can see denoted here. And then it's going to be going up it's going up because that shear stress is clockwise of 5 KSI. So that is how we have that. It's always going to be on the edge of the circle. Do the same for the sigma y. It's going to be 4 and then 5 counterclockwise for shear stress. As we can see, this is a counterclockwise rotation. And then you draw a line through the two, as this represents the current stress elements, like line that it's on. Now, another key note is the angle on the Mohs circle from our current stress element to the principal stress element is going to be 2 theta p. And we have to solve for all these. And then to the max in-plane shear stress element, it's going to be 2 theta s. So 2 theta s plus 2 theta p equals 90 degrees. That should have been covered in your classes. So that's just review a bit. So we now have to figure out the principal stresses. So to do principal stress, it is going to be this long equation, but it's really broken down to be simple. It's just going to be the center plus or minus the radius. This makes sense because if you look at the center here, the 2 principal stresses are going to be over here. That's going to be principal stress 1 and then principal stress 2. So doing the work center, which is 8 minus 6.4, that's going to give you 1.6 KSI, because we figured out the radius to be 6.4. And then to figure out sigma P1, it's going to be 8 plus 6.4. That will work out to be 14.4 KSI. Also good to note, sigma P1 is sigma 1 as well. They're the same meaning, essentially. Okay, next, so we just determined the principal stresses. Now we should probably determine this theta p that actually gets us to that principal stress. So theta p, it's just another equation. It's just going to be tan 2 theta p equals this. Working through it, you figure out theta p is going to equal tan negative 1 of 2 tau xy over sigma x minus sigma y, multiply it by 1/2. It works out to 25.67 degrees. So that's important. So this value right here is just going to be roughly 51.2, roughly. but that's going to be 2 theta p. To figure out theta s, it's going to be tan -1. It's the same equation. It's a different equation, but all these values are already given to you in that initial stress element. It's going to work out to -19.33 degrees. So what's nice is this gives a negative, this gives a positive degree angle. It shows 45 degrees apart, which is always true. That's kind of like a mid-check in your exam. If they're not 45 degrees apart, something went wrong in the middle. And then we can see that value over here. So working on that, we now have our principal stresses. Now we have to determine the max in-plane shear stress. Max in-plane shear stress is actually just going to equal the radius. And this makes sense because since the Mohs circle is always going to be along the x-axis, the max shear stress is just going to be when it's from 0, like r minus 0. So tau of s is just going to equal 6.4. And this will be in either direction, but it's going to be 6.4 clockwise in this orientation. And then going forward, they're going to show on a properly oriented stress element for both of those. So here we have the principal stress element. So looking here, we have to rotate, this is our current element, we have to rotate clockwise to reach this principal stress element. So how we draw this is, this shows the traditional x-axis, and we rotated this box clockwise, downward, per se, to reach that principal stress. And this rotation does is only theta p, not 2 theta p, just theta p, which is going to be 25.67 degrees. And then we can sub in sigma p1, or the principal stress 1, is going to be 14.4 ksi, as we already found, which is in tension because all these values are positive. And then sigma p2 is going to be 1.6 ksi. Now, how to know which direction they're acting? Here from the beginning, this 12 is associated with sigma x. As we rotate this direction, this sigma x becomes sigma p1, that first principal stress we found. And this sigma y, as we rotate clockwise, becomes that principal stress 2 of 1.6. So this actually represents like the sigma y value associated and sigma x. That's how you know which direction they're acting. And because this now falls on the x-axis, there is no shear stress. So that is the stress element for a principal stress. Moving on, now you have to do the stress element for max in-plane shear. So to get there, we actually have to rotate counterclockwise to reach this. So that angle we already found was going to be 19.33 degrees. So we have to rotate counterclockwise upwards. So here you have the current, wrong thing. Here you have the current x-axis, and then you have to rotate upwards of 19.33 degrees to reach that max in-plane shear stress. So now you're kind of wondering what's going on here. So that normal stress associated is just going to be the center because there's only one normal stress associated. It's not like there's two like before. There's just one, which is just going to be 8. So that means the normal stress across both the x and y direction of that stress element is just going to be tensile of 8 ksi, as represented down here. You have 8 ksi acting all directions. And now, for the shear stress, because you have to rotate, because you're rotating up, it's going to show a clockwise direction. So we're rotating up here clockwise. So it's going to be 6.4 clockwise for sigma x. Because technically, they're all equal to 8. However, this is still associated with the sigma x value. So the sigma x has to rotate up, meaning for the sigma x, it's going to be clockwise of 6.4. And that is shown here because this technically, this side of the element is still like associated with sigma x, and this is associated with sigma y. And it's going to be clockwise of that 6.4 ksi, clockwise rotation. For sigma y, it's going to be counterclockwise. And that is just because of how this one is shown. So that solves the first 4 problems. So looking at here, we have the 3 favorite theories. So we got the maximum principal stress, the maximum, the Tresca theory, and then finally the von Mises. So for this one, we're going to have to solve, let's do the max principal stress theory first. This one's pretty straightforward. So you can do max sigma 1 or sigma 2. So we clearly know sigma 1 as related as the principal stress is equal to sigma 1 is 14.4. So you're going to get, for the first one, 30 divided by 14.4. And I also got this 30. I didn't clarify before, but I just said steel, so the yield safety is going to be 30 KSI. Or the yield stress is going to be 30 KSI. So 30 KSI over 14.4 KSI. That gives you a safety factor of 2.083. Okay, that's going to be your number 1. Now let's do the Tresca theory. So maximum, the tau max is going to equal max of sigma 1 minus sigma 2 over 2. So basically figuring out the max of these. This is where the sigma 3 comes into play. So looking at our Mohs circle, basically it's figuring out the max, either this distance, sigma 1 to sigma 2, this distance, sigma 2 to sigma 1, or sigma 3 to sigma 1. So obviously you can visually see sigma 3 to the principal stress 1, or sigma 1, is going to equal 14.4, because it's going to be 14.4 minus 0. Now let's say it was, this circle went across the origin, it wouldn't be sigma 3 anymore. It would actually be sigma 2 to sigma p1. So that is why it's important to also consider this value here, and always draw on your Mohs circle. So for the next one, for Tresca, it's going to equal 14.4 minus 0 over 2, which is going to equal 7.2. And then you're going to evaluate this value compared to SY divided by 2. And you're going to realize here pretty quickly, that's just going to be 30 over 2, which equals 15. So 15 over 7.2, you guessed it, equals 2.083 KSI, or not, no KSIs, no values, is its safety factor for Tresca. And that just makes sense because it's the same ratio. So that's number 2. And then finally, the third one, it's going to be the von Mises. It's the most common one, and it's the one most used because this one tends to be overly conservative. Obviously, this is per question. This one's overly conservative. This one's usually not conservative enough. This one's like just right in the middle. And this is going to be von Mises. You have to figure out this, and then just compare it to the safety or the yield strength. And that is all there is to this part. So it's going to equal the square root 14.4 squared minus 14.4 times 1.6 plus 1.6 squared. And that just comes from this equation. This turns out to be 13.67 KSI. Now you're going to compare this to the yield strength. So 30 divided by 13.67 equals 2.19 as its safety factor. So those are your 3 safety factors. This one for Tresca, this one from the principal stress, they're the same. And then finally, the von Mises. Those are your 3 types of failure theories and how you can figure out the safety factor for each of them. Through that, we have now solved the final part to this question. All right, so in the end, we covered Mohs circle, the principal stress, the max in-plane shear stress, and the properly oriented stress elements. Also, the safety factors for all 3 stress failure theories. I hope this was useful. Please like, subscribe if you liked it. If you have any tips for others, comment down below, and have a great day and best of luck on your exams.